fokus pada kemampuan akademik saja. Kami juga mewadahi mahasiswa untuk berekspresi, berinovasi, serta mengembangkan kreativitas melalui berbagai sarana organisasi dan pengembangan diri. Didukung jaringan kerjasama yang luas, juga fasilitas kampus yang modern. Semuanya itu menjadikan proses pendidikan yang menyenangkan, efektif, dan berdampak. Dari sinilah terlahir generasi muda yang akan menginspirasi dunia. Universitas Kristen Maranatha, kampus generasi inspirasi.
Good morning, ladies and gentlemen, distinguished speaker and all participants joining us. Welcome to the second day of 21st International Conference on Mobility, Sensing and Networking, MSN 2025. This conference is proudly organized by the IDS Lab in collaboration with Maranatha Christian University. On this occasion, on behalf of the conference team, we would like to express our gratitude for your presence. It is a pleasure to gather all of you here in this morning, December 4th, 2025, at Maranatha Christian University, Bandung for today's conference. Before we start, you may want to scan the QR codes on the screen for the attendance and also for the rundown for today. We will continue with the keynote speaker session with a rubric and follow it with the parallel presentations. For the keynote speaker that we have today, Professor Jong-gil Ko from Yonsei University, Korea. As the adjunct professor, Postech AI Graduate School, guest professor from Keio University, Japan. Former Associate Vice President for Information and Communications, Yonsei from 2022 to 2024. Chair Department of Integrated Information Technology from Yonsei University. PhD Computer Science, Johns Hopkins University from 2012. Professor Jinko as the Senior Researcher from ETRI 2012 to 2015. Assistant Professor in Azhou University 2015 and 2019. And as editorial roles on the editorial boards from ACM, IMWUT, IEEE TMC, ACM TIOT, and IEEE TQE. With other words, Abel Woolman Fellowship from Johns Hopkins University and commendation by Deputy Prime Minister and Minister of Education of Korea. Let us welcome to the stage Professor Jong-gil Ko from Yonsei University, Korea.
All right, thank you. Thank you. That was yeah, awesome. Thank you. Thank you. Can I have my slides up, please? Yes, thank you for the overwhelming introduction. I really like that first slide. I've never gotten that from a conference before. So is this my slide? No, can I get my slides, please? Yes, there we go. All right, so thank you again for the introduction. My name is Jong-gil Ko. I am a associate professor at Yonsei University in Seoul, Korea. So in today's talk for about 45 to 50 minutes, I'm going to be talking about some of the research that we've been doing recently at our research group at Yonsei. And I've titled the talk as Migrating the Intelligence from the Cloud to the Users. So you can get a feeling of what I'm going to be talking about as we kind of discuss how we take the AI intelligence that we typically have on the servers down to the actual user devices. I'm not sure if this is working. Yes, that's me, but I think I had a fancier slide introducing me 2 slides before this, so I'm just going to move on to my next slide. Why isn't this working? Is this supposed to work? Yes, yes. Hold on. Can you go back? Yes. Yes. Hold on. I'm a computer scientist. I should be able to do this. All right. So these are some of the things that our research groups, these are some of the projects that's happening in our research group or has happened in our research group. So our research group focuses on sensing technologies. How can we enable different sensing technologies to make new applications for users? One of the systems that we recently worked on is a system called PowDew that you see on top over there. It was the Mobius 2024 Best Paper Award. What we did there was we tried to identify counterfeit baby powders. So I'm pretty sure most of you have not been married yet, especially the students here. When we have babies, they can't start eating meat on the first day. We start with something called a baby formula. And the problem is, as parents, we get really sensitive about what's inside this formula. We're very sensitive about the authenticity of this formula. And there have been incidents where you have fake formula and you feed your children these wrong formulas and things go terribly wrong. So what we did in that system is try to use vision sensing to identify counterfeit formulas that are not what they are advertised as. Right? So that's a Mobius paper, so take a look at that if you're interested. The one you see on the top right is our paper from UbiComp 2020, and it's a system called Heartquake. So do we all know what ECG is? ECG or EKG, electrocardiograms? How many of you have heard of ECG? EKG? Something like that, yes. So it's basically the amount of electricity that's flowing inside your body to run your heart, right? And obviously, to capture electricity in your body, you need leads to connect to your body. And it's all puffy and wiry and everything. It's very complicated. And if you have some kind of chronic disease that you need to monitor, in conditions where you need to monitor yourself continuously, it's especially uncomfortable, let's say, when you're trying to get some sleep, right? So what we do here is we try to identify the vibrations that your heart is generating, and we try to find the correlation between the electric signals that make your heart beat and the physical vibration signals that your heart is generating. And we go under the hypothesis that if the ECG changes its pattern, the motion of your heart or the vibration of your heart is also going to show a different pattern as well. Therefore, if we detect that your heart is beating physically in a different way, the vibration changes, then that correlates to changes in the ECG. Therefore, what we do is we kind of detect or predict what the ECG would be using only the vibrations. What this means is you can install a accelerometer on your bed, and without connecting anything to your body, just capture the vibration signals that are on the accelerometer and infer what the ECG would be without anything connected to your body. And then we have a bunch of these interesting systems that are taking place, mostly related to humans, mostly related to mobile sensing and how we use intelligence or AI algorithms to enable these different types of applications. Today, among all these different types of systems, I'm going to go a little bit deeper into a slightly older paper that we have from Census 2019, and this is a system that we call Vitamon. So the purpose of Vitamon is, again, to capture vital signs, capture physiological signals without connecting any sensors to your body, right? And the sensing modality that we try to capture here is something called heart rate variability. So you know what heart rate is, right? So my heart is beating like 60 beats per minute, right? That's heart rate. Now, heart rate variability is basically how your heart beats, the interval between your heartbeats variate. So if you're a perfectly healthy person in a perfectly comfortable state, your heart is going to beat like doom, 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 in an extremely regular pattern. On the other hand, if you have things like arrhythmia, or if you are nervous, or if you're stressed out about something, your heart is going to have a different beat. It's going to go boom, 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 boom. It's going to have this variability in the intervals. It's going to be the same 60 beats per minute, but you're going to have a different interval between the beats, right? And by capturing this so-called heart rate variability, what we can do is we can, of course, as I said, we can detect arrhythmia, things, disorders to your heart, and at the same time we can detect stress levels. If you're stressed about something, if you're overly focusing on something, we can notice that the heartbeat is going to change irregularly. And that's what we're trying to capture here. Now, the thing is, in order to capture heart rate, you typically have a sensor. I'm pretty sure a lot of you have smart watches, and these smart watches have something called PPG sensors, plethysmography sensors, and these sensors are used to capture your heart rate by identifying when exactly your heart is actually beating using optical sensors. Now, what we wanted to do was take this out of the picture, and maybe can we do this in a more easier way? So what we use is the physical characteristics of blood. Now, how many of you can tell me what color is your blood? Red, yes, thank you. A very easy question. Yes, and okay, here's a harder question. Christmas is coming up. So what is the opposite color of red? Blue, it's more Christmas. Green, it's more of a greenish blue. It's more close to green than blue. So that's why the Christmas colors look very pretty, because we have opposite colors there, right? And okay, third question, what colors does your smartphone camera capture? It captures all the colors, right? It captures all the colors using the 3 basic colors of light, which is, yes, we have them in different orders, but I got RGB there, right? So, what we're going to do in Vitamon is, so if your heart pumps, one of the first places that a bulk of blood goes into is going to be your brain. So, in order to get to your brain, it's going to have to pass through your face, right? And so, therefore, every second or so, red blood is pumping up from our heart through our faces to the brain. That's what's happening. That's why you're living. Now, if we analyze, if we have RGB, so here's what we're going to do. We're going to just look at the camera, and oh, okay, that's my heart rate. That's what we're trying to do. Right? I'm not going to do anything else. I'm just going to look at my camera and capture RGB, capture the heart rate or the heart rate variability. How do we do this? Blood is red. I'm capturing RGB. And if I remove the red channel and I remove the blue channel, just keep the green channel, which is the opposite color of red, and analyze the pictures the images that I capture of my face, I'm going to see subtle differences in the face, in the color distributions every time my blood pumps. Because we have veins on our facial regions, and when the blood pumps, it's obviously going to turn reddish. We can't see it. It'd be very scary if I can see your blood pumping right now, but we can't see it with our naked eye. But if we use the camera and we analyze the color distributions of the green channel very carefully, we can start understanding when the blood is pumping, right? Now, we can get a rough picture because our front camera does not run at 120 frames per second. It's running at 15 to 30 frames per second because it's only used for selfies. The purpose of the front camera is for selfies and self-identification. It's not, getting like HD videos. So we have a very rough estimate of when the heart is beating, and we're going to run this through a deep learning model to understand that the blood is going to continuously and sequentially flow from your throat to your neck to your chins and up to the forehead, right? It kind of flows continuously. So using the deep learning model, we're going to understand that flow and capture what the actual heart rate variability is. And these are our results. I'm not here to brag that we have good results. What I want you to focus on here is that we have two different plots here. We have two different bars, so to speak. So one, we have the personalized model, and one, we have something called the general model. Now, typically when you're doing these types of healthcare research, you want to make a model that is generic, right? You want to build a model and you want to deploy it and you want to make sure it works, right? But on the other hand, you want an accurate model. And when you want an accurate model, because everyone has a different anatomy of their facial blood veins, by training the model just a little bit with your personal data, you can definitely get a much less error, a better performance compared to a general model. So for many of the applications that we use on our smartphones, many of the sensing applications that we have, if we have the capability to slightly train the model on the device, instead of using a perfectly generic model, if we can just fine-tune that model just a little bit to fit my own purposes, we get a much better accuracy. Now the question is, we have these heavy deep learning models on our phones. Of course, we have our MPUs and GPUs, but still they're pretty heavy for a smartphone. How can we train these models on an actual smartphone rather than just performing inference? So this is where on-device AI kicks in, and on-device AI not only for inference, on-device AI for model training on our devices. Now, if we were to enable this on-device AI and model training on our devices directly, we can enable a various set of applications. We have voice assistants. Everybody has different voices, so you can adjust the model to fit your voice and your speaking style. Predictive text. Everyone has different vocabulary that they prefer. Facial recognition, photo classification. All these personalized services we can definitely improve if we have the capability to train these models on the device, not just inference. So what we eventually want to do is, instead of the current model that we have, where we say, I have some private data that I have on my phone, I'm just going to dump all this data to Google and let Google do all the magic and then get a model. What we want to do is forget about Google. I'm going to capture the data on my phone, train the model on my phone, and just use the model for myself, right? Because this way, we can definitely make the system more efficient by reducing the amount of communication. And also at the same time, we can also preserve the privacy of the data that we're collecting on our smartphones. So there were two questions when we started working on this project. The first is, come on, we're using a smartphone GPU. This is a crappy GPU. It's probably not going to run. The answer is it does run. It's just extremely slow. It's about 10 times slower compared to server scale GPUs. Now, slow is not a problem. Slow just requires patience, right? The bigger problem is actually the memory bottleneck, right? Because we have limited memory inside our smartphone GPUs or mobile GPUs, the training process, which is an extremely memory intensive process, cannot complete. Right? So the first part, the CPU and GPU power being less, is a matter of efficiency. It's a matter of, can I do this fast? Is it going to take a long time? The second problem of memory capacity is a Boolean problem of, can I do this or not? Right? So what we focused on is the second problem, where we say, okay, even if we have a limited amount of memory, can we make this training happen on the phone? Now, here's an example on the iPhone 13. What you see here is inference takes up this amount of memory, teeny tiny, compared to a batch size 8 training of a ResNet 50 model running on a phone. It's going to use up 3 gigabytes of your memory. Now, our phones typically have about 8 gigabytes of memory. Some fancier devices have 16 gigabytes. So maybe this is doable, but still, you have your operating system running, you have your apps running, you have all these sensors running in the background, and you want to give up 3 gigabytes of memory to your phone for just simple model training? No, we don't want to do that. So how can we do this? How can we reduce that memory overhead? So first of all, let's formulate this into an actual problem, which we define as the memory blow-up problem. So when you're doing inference, we don't require too much memory, as we saw here, mainly because when you're doing inference, you just can drop all the memory that you've already used. Once you're done with that state, you're just dropping the memory. So life is good. It takes some memory to compute something, and then I forget about it. right? So life is good after you kind of progress. The problem with training is we have something called a back propagation, meaning that we need to go through the entire graph and then come back and start making changes to our model weights. Therefore, as the model progresses, it has to keep everything inside the memory so that when I come back, I can start making changes, right? This is what causes training to consume a significant amount of more amount of memory compared to inference. And this is the problem that we want to try and solve. There have been approaches that say that we need more efficient training on server scale devices, but they assume powerful GPUs, they assume they have host side memory, and what they try to do is they try to do memory efficient optimal scheduling, right? However, we're living in the world of a smartphone, which we have low power GPUs, and these GPUs are typically made in a form factor of SoC, system on chips, which means that these GPUs are going to be sharing the memory between the processor and the GPU. So you have a unified memory architecture. And you're using your smartphones in a very different, everyone's using their smartphones in a very different way. GPUs on a server, their sole goal is to run deep learning models. The GPUs on your phone, the main purpose that the GPU is there is not to run a deep learning model. It's to run your graphics applications that makes your smartphone run. So it's really heterogeneous and hard to expect how much GPU capability, memory capability that we actually have. So these are the problems. So the bottom line is that after all considering this, we designed something called SAGE. And this, what SAGE does is it basically reduces the memory usage by about 20 times. And it achieves a practical throughput and supports semi-state-of-the-art deep learning training. This paper was presented at Mobius 2022, so if you're interested, you can go there. And the basic idea is that we're going to integrate 4 different schemes, just you know, amalgate basically 4 different schemes to reduce the memory as much as we can. First thing that we do is if your deep learning model had 100 gradients, we want to reduce that down to 20, right? And for each of the gradients, if each of the gradients were, I don't know, 5 kilobytes, we want to reduce them down to 500 bytes, right? Those are the first 2 approaches. We want fewer gradients and we want smaller gradients. That's one way of reducing the memory. Those are 2 ways of reducing the memory. How do we do this? So basically, if you represent your neural network as a graph, what you're going to notice is that, so it's kind of small, but what you see here is function A, its output is input to function B, right? And then you have an input and an output of these 2. What we do is we just combine these 2 functions together so that we reduce the amount of computing operations that happen and the amount of things that we need to keep in the memory. We call this graph fusion, and by doing that, we can reduce the number of gradients. Smaller gradients is easier because we all do quantization, and using quantization, we can do the same thing. Now, this is something that we do in offline mode when we're not in runtime. And in runtime, what we do is, again, 2 things. The first approach is something called micro-batching. So instead of running an 8 batch at once, we're going to reduce that to 2. We're going to reduce it to 4. And then we're going to run smaller batches, which is going to reduce the amount of memory. And at the same time, in the worst case, when we tried everything and we still don't have enough memory, we're going to start evicting things out of the memory. We're just going to say, I know you're in the memory, but I think it's easier to recompute this part rather than to keep this in the memory. So I'm just going to take it out of the memory, and later on when I need it in the back propagation process, I'm just going to recompute it, right? So that's what we try to do. And by doing so, we're reducing that over 3 gig down to that by about 20 times. So this is a significant amount of reduction in memory. And one of the experiments that I do want to share from this work is when we played a game with the Galaxy S10 phone. So the Galaxy S10 phone is a fairly old phone, but it's still being used by a lot of grandparents. I'm sorry if you're using an S10. I'm pretty sure. But what we do is we intentionally control the amount of memory that our deep learning model training can use from 1 gigabyte to 2 gigabyte, 1 gigabyte, 2 gig, 1 gig, 2 gig, 1 gig, 2 gig. And then we say, train the model. So what happens is this. This is the actual memory usage of Sage. And what you see here is from 0, it starts using up the memory as it starts training the model. And then it's going to hit the memory wall. Once it hits the first memory wall, it's going to start with batch size 32. Once it hits the first memory wall, it's going to say, okay, my bad. So let's reduce the batch size to 20. And then it's going to operate in that phase, and then it's going to use up memory, and then hit another memory wall. And then it's going to say, hey, 20 is not going to work. Let's reduce it down to 14. And it's going to, and at 14, it's going to say, if I go any lower than this, I'm going to, my GPU is going to be underutilized. So this is the tipping point. So from this on, whenever we meet a memory wall, it's going to do the evicting scheme. We're going to start checking out some of the things that we have inside our memory. So instead of running 32 as a whole, it's divided it into 14, 14, and 4 microbatches, and then we get our result. As you can see, this is one round of training. One sample, one round of training. It takes about 5 seconds on the S10. So, controversial, some might say this is too long, some might say it's better than we thought. With the S25s, it's definitely going to be faster because we have better GPUs. But what this tells you is that it's not impossible to train, right? We can start training our devices, our models on the devices that we have. Now, after this research, my research group started asking more questions about this on-device training per se. And we wanted to take a more practical example. Let's say you're an app developer. And you deploy your app in the field. And your app has this awesome AI thing in it, right? How many users do you want to be using your system? 5? Hell no. You don't want 5, 10 people to be using your system. You want hundreds, you want thousands, you want millions of people using your system, right? Which means that whatever AI model you designed, the same model is going to be, hopefully in the successful case of your startup, be used by hundreds, thousands, and millions of people, right? So we start asking the question, why can't these guys collaborate? Okay, we're doing on-device training, but the amount of on-device data that I can actually collect over a certain period of time is very limited. Why can't we get these models to start collaborating with each other and build a better model? So in the old days, everyone would send their data to the server, so the server will have knowledge from, say, 1,000 users, and it would train based on that. Now we're doing it online, on device, which means that you're only training for one person. And the accuracy of your model is going to suffer, definitely, because you have less data. So how can we do this? How can we gather the data from so many people, but not sacrifice our data security or data privacy? Our answer was federated learning. What we did was we started looking into fed learning. What fed learning does is basically the server is going to say, okay, here's a model, and I'm going to select the clients. So the selected clients would basically be the users of the app. And I'm going to share this model with you. This is the model that your app is going to be using. What I want you to do is use your own data to perform your own local updates, local training on the data. And then, don't stop there. Don't stop there. What I want you to do is I want you to share the model parameters with me. Right? Not the data. Don't give me the data because that's privacy sensitive. Just give me the model parameters, and I'm going to aggregate the model parameters, and I'm going to distribute these model updates again. Right? This means that I am training with my own data, but as soon as I share my parameters with the server is going to aggregate the model weights from hundreds of millions of users. Therefore, the model is going to be stronger, hopefully more accurate, and I'm going to get that model back. By contributing this much, I'm gaining this much. Right? That's the concept of federated learning. And it's really fit for things like healthcare applications. Because, for example, let's say I have a certain type of disease. That disease does not come every day. It's from time to time I get those incidents. So over the course of the year, maybe I get like 6 events. But let's say 1 million people around the world are sharing the same disease. Now you have 6 million samples that you can use to train, right? Without sharing your actual data. So that's fed learning. So in fed learning, what people focus on is basically how can we share the models in a more efficient way? Because these models are big. How can we share the model parameters in a more efficient way? What we looked at is the attention mechanism. I'm pretty sure all of you who are into deep learning know attention mechanisms by now, because they're the basis of the transformers that we use in many of the model architectures. But what the attention algorithm does is, instead of saying, this is a lighthouse, it's going to say, this is a lighthouse because I think this part is important. If you look at this part is the part that made me focus, and that part is the one that made me determine that this was a lighthouse, right? So it puts focus on contextually important parts of your input, right? So what we do is we put the attention mechanism onto the model itself. Instead of attention on an image, we put attention on the model weights. And when the model weights start to change, hopefully the attention mechanism can capture the fact that, oh, this part changed. So this is the important part, right? And that's exactly what we do. So we have the baseline DNN for your federated learning process. We put 3 attention layers, one in the first half, one in the second half, and another that covers the entire model. And what the focus of that attention layer is to identify which parts of this model weights, is important. Which part of these model weights should I be sharing with the server so that the server can aggregate, right? So that's what we do. So instead of sharing the entire model parameters, what we do is we just share the attention weights of these 3 attention modules that we have on the model, on the baseline DNN. This significantly reduces the amount of communication that we need to do with the server to share our model information. And this is the result that we see. So Fed attend is what you're looking at, the red line here. In terms of model accuracy, we have the highest performance compared to all the other baselines. Communication cost, you can definitely see that it reduced significantly, mainly because we're not sharing the entire weights. The amount of local computation that we need to do, the amount of server-side computation that needs to take place, all reduces because we are reducing the amount of information and kind of abstracting into a high entropy piece rather than sharing a larger piece of information. Right? Another benefit of this attention mechanism is that you can start federated learning for all different types of model architectures now. Even if you have a very complex or big model as the baseline fed learning model, because you're able to share the essential parts of the model instead of the entire model itself, you can enable all fed learning on all these different types of baseline models. So this is so usually in our group, we, after we're done with our server-side evaluations, we like to put it on the actual devices to see if it actually runs. Here, in this case, we validated using a Raspberry Pi, Jetson Nanos, and Jetson TX2s, and we see exactly what we expect to see. Now, what Sage did, what Vitamon did, is it gave us a nice motivation of why we need on-device training. What Sage did was it gave us a platform to start actual training on resource-constrained GPUs. And what Fed Attend did is basically give us a way to efficiently share federated learning model parameters with a server. Now, we took this another step further to be a little bit more practical. Okay, raise of hands. How many guys use an iPhone? Proud user of an iPhone? iPhone 15? 16? 17? Whew! You guys have a better phone than I do. I do research in mobile computing and you guys have a better phone than I do. Well, see, it's different, right? I'm pretty sure you don't have an iPhone 17 either. Galaxy S25s. S24s, looks like Samsung's not doing very well in Indonesia. So the bottom line is that we all have different phones. And the capabilities of our phone is different. Obviously, compared to the rich students here with the iPhone 17s, my mobile GPU is obviously more crappier, right? And you have a better computation power than I do, right? But what if I said, you know what? What's your name? Maresa. Okay, Maresa. I'm an app developer. And I'm going to give you an app that you love, but the model inside there, you know, it really maximizes the performance of an iPhone 13. I know you have a 17, but we're not going to give you a good model to run on 17, because if it's a model that runs on 17, it's not going to run on the 13. You also have 13, okay, shit. Let's say you don't, you rich girl. Let's say you don't, right? How would you feel if I said, I'm going to give you a crappy model because I need to consider everyone else? Sure, I'd like to be nice, but you know, I bought this phone for a reason, right? I bought this phone because I want the high performance. I want a better model that can fit me. That's the typical way of thinking, right? So, if there are heterogeneous models distributed over different platforms, these devices are going to have different capabilities. And the optimal model size or the optimal model capacity for each of these smartphone models are going to be different. Some are going to have high power. Maybe we can give them some better models. Some are going to have lower power. So maybe we can give models that fit these GPUs, right? It's not perfectly economically most efficient way to do it, but in the ideal world, this is what we're going to do, right? You have a good GPU, use a good model. You have a crappy GPU, use a crappy model, right? That's, well, welcome to the world. So this is exactly what we have. This is the world that we have. And this is, you know, it totally makes sense. The problem is, if you look at Fed learning, we operated under the assumption that your model, my model, and your model are the same, because we need to aggregate the parameters together. What if you have 5 layers of convolution layers, I have 3 layers of convolution layers, you have 1 layer of convolution layer? How are we going to aggregate these parameters together? It's just not possible, right? So what this means is that you can only aggregate with iPhone 17s, I can only aggregate with iPhone 16s, and he can aggregate with whatever he has, right? So we have a problem here. How can we solve this problem? And this is exactly the problem that we try to solve. So we have powerful devices and we have weak devices, all with different GPU capabilities. Powerful devices are going to have powerful models. Less fortunate devices are going to have less fortunate models. Now, if we start doing Fed learning here, the more powerful model is going to give me 3 layers of information in this example, right? The intermediate model, the one in the middle, is going to give me 2 layers of information. The most weakest model is going to give me 1 layer of information, right? How do we Fed learn? How do we aggregate these parameters in federated learning? The easiest way is just add them together. Just sum it up. That I have 3 for layer 1, so good for you, layer 1. Layer 2, you're missing 1. You got 2. Well, better than nothing. Layer 3, well, rich guy, you're the only one having this layer, so you have nothing to aggregate with. This is the easiest way to aggregate heterogeneous models. The problem is, once we start doing this, we have something called information disparity, right? And information disparity means basically, come on, man, I bought a good phone for a reason, and I don't have anyone to benefit from by having this model. So what problem does this cause? If you look at the results because of information disparity, this is the case if under the unrealistic scenario that everyone has a good phone and everyone is running the full 3-layer model. This is the performance that we get in Fed learning. And then The second line, the blue line that you see here, is saying that, okay, let's be fair. Let's just use the crappiest model. Let's just use the worst model, everybody. I know you have power left, but just forget about it. We're just going to use a crappy model. And definitely, we're going to lose some accuracy here, right? Because we're not using a good enough model. Now, what if we do that aggregation that we just saw? Just put together a thing. Ideally, what we want to see is we want to see a line somewhere in the middle here, right? Between these two, because we have a mixture of these models. But here's what we actually get. We get a crash in the data, right? So we need to fix something. Something's gone wrong here. So information disparity, because we're missing those higher layers, shows a significant performance degrade because the top layers of your high performance model is not synchronized with the other layers that are being aggregated with the other parts. So we have a problem here. How can we solve this? We're missing layers. Easiest way is to buy everyone a good phone, but that's not practical. So what do? We use something called a hypernetwork. What the hypernetwork is a very interesting neural network architecture, and it's designed to generate new model architectures. It's designed to estimate and generate weights for new models, right? So this is exactly what we use. We're going to say, okay, I am missing a few layers here. So Mr. Hypernetwork, can you generate a few layers for me? Can you make some fake weights for me? And so that I can imagine that there's something there, right? That's what we do. But what we need to make sure that the hypernetwork is kind of tailored to our application, right? So what we do is we take some of the samples. For example, I'm going to go back to the example here. What we're going to do is we're going to take, we're going to take these weights and say, hey, so if layer 1 and layer 2 look like this, layer 3 is going to look like this. Can you generate a layer 3 if layer 1 and layer 2 look like this? Solve this puzzle. If layer 1 and layer 2 look like this, if layer 1 looks like this, layer 2 looks like this, layer 1 looks like this, layer 2 looks like this, can you generate a layer 2 for me? So we're going to use the samples that we have for that round and generate samples using a hypernetwork. The problem with hypernetworks is that they are extremely heavy, even on servers. It takes more than 10 hours to generate a few weights. So what we do is, details in our paper, but what we do is we basically use something called low rank factorization, a bunch of fancy math, to reduce the complexity of the hypernetworks so that the hypernetworks are operatable on server scale devices for this purpose. So eventually what happens is each of the devices are going to have different model sizes, models of different sizes, and it's going to do a model update as in federated learning. The hypernetwork is going to be generating the weights for the aggregation process, and then using the real and fake weights all together, we're going to start aggregating things in place. And then, at this point, finally, we get the result that we expect. This tall line that you see here is the unrealistic case when everyone is using a great model. This line that you see here, the third line you see here, is the unfortunate case when everyone has to use a bad model. And what we see is a performance somewhere in between there. Right? And in terms of hypernetwork, we're reducing the complexity of the hypernetwork down to like 99%. So that's extremely low. Hold on, I'm sorry. Yeah. All right. And again, validation on a real testbed, we see exactly what we want. Again, due to the lack of time, more details in our Census 2024 paper. All right, so I'm going to wrap up the talk with the hope that we're going to have some questions. I know I'm at an Asian university and then mostly Asian audience of students, which I seldomly get any questions, but I'm just going to cross my fingers. So to sum up, so we started off with Vitamon as an application, motivating application. Why do we need to do online training? And then we moved on to, okay, can we do online training The first answer was no, but now the answer is yes. Right? By taming the memory usage a little bit, we can do online training. The next question that we asked was, hey, if we have a lot of these devices that are basically using the same model, do we have a way to kind of fully exploit the capabilities of this commonality in AI model usage? And we have federated learning as an answer for that. And then the next question, the final question that we asked is, in practical cases, everyone has a different phone. How can we enable heterogeneous federated learning? And we have our hyper-network-based solution for that. So that's most of my talk. And the last slide that I want to share is this. So basically, I'm pretty sure we all know that the mobile GPUs are not in par with what we use on the server, right? And this is a perfect example. So this, for example, it's not most recent, but the NVIDIA RTX 4080, not a bad GPU. We still use it for lots of applications. 4080 is, the benchmark score is somewhere around here. The M2 Ultra, which is used in MacBooks, is somewhere down here. And pretty sure a little bit weaker than the M2 Ultra is the M2, which is used, so this is MacBook Pro, and this is MacBook. And when you go down to a MacBook Pro, this is going to be probably a little bit lower than M2 Ultra, and we have a score of 7,000 here. And the Apple A16 processor, which is the processor that goes into iPhone 15 Pros, is approximately half of that score, right? So if you sum this up, we're somewhere around 10 to 15 times slower on the iPhone 15 compared to a 4080 GPU, right? 10 to 15 times. So some may think this is too much. I believe this is surprisingly fast. So we have a lot of opportunities in exploiting the full capabilities of the mobile GPUs that we have. Of course, again, as I mentioned in my talk, mobile GPUs are not designed for deep learning. They're designed to support your graphics applications that you have on your phone. But graphics applications, even if they're running at 60 frames per second, you have that idle time. How can we use that idle time and that processing power to enable different types of applications is a question that we definitely have to ask as mobile systems researchers. And the fact that we're very tightly coupled with the sensing interface, the user interface, and the applications on the phone, on the GPU, enables a lot of different types of interesting applications that we can further research. So thank you to all these institutions for giving me the money to do this research. I think this is a mandatory slide. And this is my research group. These are my students that actually performed the research. So the first project that I introduced was Vitamon, and this was done by one of my postdocs. He's a Vietnamese postdoc. He actually is in France right now. He's at a French AI startup. He was the Vitamon guy. And then the second one was Fed Attention. Fed Attention was done by Jaeon Park. He's a PhD graduate from our group. He's now an assistant professor at Dankook University in Korea. And then the third and fourth projects were done by Ki-chang and Eugene, who are still PhD students in our group. Hopefully they'll be graduating sometime later this year. So these are the real, the brain power behind my research group. And I'd like to thank them, and I'd also like to thank you for your attention today and the invitation to the conference. Thank you very much.
Thank you, Professor Jong-kil Ko, for a meaningful presentation for today. For participants here, if you have any question, you may want to raise your hand.
Again, I'm not surprised.
Thank you. I'm not Asian.
You're not Asian, no.
Yeah, I mean, thank you for the great talk. I was just wondering, what difference can you make between, real training on the device and some kind of fine-tuning? Because you mentioned that...
You said real training and...
And fine-tuning.
Fine-tuning,
Yeah, because you mentioned that at the beginning of your talk.
So, training a model from scratch, I think that's what you mean by real training.
Right.
Is possible, but you would be crazy to do that due to many reasons, but two off the top of my head right now. First of all, I'm pretty sure you don't have enough samples to fully train a decent sized model on your phone. And number two, even if you had the data, the training time is going to be significantly high. It's going to be possible. It's going to be possible, but your phone is going to have to be plugged in on your table for a very long time while you don't use your phone, right? So I think real training or training from scratch is definitely possible, but more practically, what you want to do is you want to take a pre-trained model and then kind of fine-tune it and just customize. That would require, depending on the application, we're looking at like 500, 1,000, maybe a couple thousand samples. Highly doable overnight, right? But if you want to train over millions of samples for a model, then that would take a significant amount of time. So the answer would be, it is possible, but why would you want to? Would be the answer.
Yeah, so basically you are talking about fine-tuning
Yes.
in your work.
Yes.
Okay. And did you try to use something like LoRa, for instance? I mean, not to change all the weights, but, small matrices?
Yes. So LoRa is a technique that can go in parallel with the approaches that we're taking. Right? LoRa is another form of abstraction, right? It's another form of abstraction. And we actually use LoRa for the hypernetwork problem, right? So the hypernetwork, in reducing the complexity, we use low-rank factorization and LoRa. So we take that approach. But for model training, we try to keep the model architecture as is, because we are under the assumption that the application developer has designed this model to be the ideal performing model for their purposes. So we don't want to touch the model architecture in different ways. Is that an answer?
Yeah.
All right. Thank you.
I have one more.
Sure.
Yeah, you mentioned something really interesting when you talk about federated learning. When you say, when you were talking about diseases, and you were saying, okay, maybe I have just 6 data, just a few data about my disease, and I want to share that with other people. But with that small amount of data, even locally, it's very hard to get a good model.
That's right.
So
that's right.
so what you are sharing, you are sharing a bunch of bad models.
Yes, yes.
And it's a very tough question.
That's right, that's right, that's right. So I guess I used an extreme example there. But as you mentioned, if you want a healthy enough model to share with different users, even under fed learning scenarios, you do need a decent amount of samples where your samples model is going to converge with that added data. So that is perfectly true. The example that I used was, it was to motivate and exaggerate the scenario.
And any way to share data? Rare data?
You mean sharing the personal data?
Yeah, but just a few. That would...
if you start breaking the assumption that you actually want to share the data, then you might as well share the data, right? But I think the whole concept of fed learning is under the assumption that you don't want to do that. So it's suitable for those type of applications. Right?
Thank you.
Awesome. I want a question from the, yes, PC chair. No, I was about to say students.
Thanks for your wonderful talk. One thing I wanted to know, you said that you have a set of heterogeneous devices, is right? So you, from your experiment, you use Raspberry doing this. So that means you own all of these devices. If like us, we are a stranger, I wouldn't, share, cooperate with others to training a particular model. So how you deal with that case?
So it is correct that one of the big challenges that fed learning is facing is the killer application, right? So we use a Raspberry Pi, we use a Jetson Nano, we use a Jetson TX2. So that shows the heterogeneity part. The problem is, who is the owner of the data? Who is the owner of the model? Is the owner of the model willing to share its knowledge with other people, right? This is beyond technology, but at the same time, as a tech-savvy person myself, if I can benefit from the sharing of my data, sharing of my model, the sharing data, I'm very skeptical. But if I can benefit from the sharing of my model, to have a better model on my perspective, in a privacy preserving way, this would be a better approach than sharing my data. Because already we're sharing a lot of data with the server. So in terms of sharing the data, we're already sharing a bunch of stuff. The question is, can we share a different thing rather than the data itself? So I think up to now, people are skeptical about sharing data, but they accept the fact that in many cases we do need to share. I think this trend is accepted among the people. And we tell the people now, instead of sharing the data, share your model. This is a more secure way of doing things. I think there will be less backfire from that approach.
Okay, thank you. Another issue is related, you say, oh, I have a model, I just participate training, is right? Because I installed the model, on one aspect, I want to, using this model doing inference service. Another one is participate, as you mentioned, model training. You make the service more accurate, is right? How you deal with, you can do both things. You use graphics memory, you use GPU or CPU resource. You're doing two things at the same time.
Yes, that's a very good question. So, if I understand your question correctly, so depending on the user, they can selectively try to do inference only, and some might do inference and training. Is that correct?
Yeah.
Yes, and therefore the amount of GPU resources that you can actually use is going to be even more heterogeneous in those cases. Is that where you're getting to?
So you are just this amount of GPU resource, is right? So if you're doing training, you are supposed to not doing, inference service.
Okay, I see.
Otherwise, you're doing inference service, you cannot participate.
Yes, I see,
in
I
training,
see.
is right? Because this online going, I cannot say, oh, I just help training. I do not do my own things.
Exactly,
right?
exactly. So in our example, we saw that one training takes 5 seconds. Let's say we do training for 100 samples. That'll take 500 seconds. And for that 500 seconds, your GPU is going to be pretty busy. So you're probably not going to be able to do any inference operations during that time, right? So what we envision is that all the training applications, fine-tuning applications will happen overnight. Another issue that we need to look at is heat, thermal heat, and also power usage, because you're running the GPU in a very intensive way. Therefore, it really doesn't make sense to start training while I'm on the train, trying to use my phone. It makes more sense when training when your phone is plugged in and at nighttime when you're in sleep mode. And that's the time when you can start using the idle resources of your GPU for training operations. And under these situations, there are less cases where the inference actually has to run. Usually real-time inference has to run when you're interacting with the phone directly. But overnight, this is not going to commonly happen.
Yeah, if offline, that's another issue. Usually you're doing so-called training. I'm presuming is incremental, training and provide more accurate service, like automatic driving, is right? So you have a new situation, you need to put in, you tuning your model, better serves the car running, avoid, accident, is that type of thing.
I mean, that's right. But I don't think we're at the stage where we can, tune it in real time and kind of get things working. We're not there yet. Yeah. But that experiment was done on the S10. So hopefully with the S25, we're a little bit more faster, and maybe we can do some level of training on the run as well. Right?
All right. Okay. Thank you very much.
All right.
Okay.
Thank you.
Bye.
Let's give another applause to Professor Jung-gil Ko from Yonsei University, Korea. We would now like to invite you to the stage to receive a certificate, which will be delivered by Dr. Meiti S.A.M.S.E. AKCA as the Head of Institution of Research and Community Service. We would now like to have a group photo. Ladies and gentlemen, please move to the middle section, fill the empty seats as the picture will be taken from the stage. Boleh yang di belakang ngisi yang tengah dulu ya. Ke tengah dulu. Yang di pinggir-pinggir. Okay, everybody get ready. Smile. 1, 2, 3. Cheese. Another one. 1, 2, 3. Another photo, please. Gesture like this. 1, 2, 3. Okay, last one for the video. We still use this gesture, but on 3 we say eyes, okay? Integrity, care, and excellence. Okay, okay. Okay, everybody get ready. Integrity, care, excellence, okay? 1, 2, 3. Integrity, care, and excellence. Thank you, thank you. After this, we will have a coffee break before our parallel session. Before we leave, please scan the QR codes on the screen for the feedback form and the rundown for today. And before we leave, there's a few announcements. The first one, the refreshment will be at the B building atau Gedung B on the 9th floor. You may want to ask the staff outside for direction. The second announcement, there will be a bus accommodation for participants from to both of the hotels at 8 a.m. in the morning. Today, we would have a gala dinner. Please stand by at 5:30 p.m., which the bus will be run from the Maranatha Christian University. And the last one, if you are interested for the Bandung tour, you may want to register at the front desk and please meet Mr. Emil. If you have any other question, you may want to ask the staff for any assistance. And please feel free to enjoy the refreshments at Gedung B. Thank you. Sorry? Oh, yeah, it's here. I think after this, we will have to... It's very good. Thank you.
What kind of study are you doing?
I learned urban planning actually.
Oh, okay. So here?
No, on different uni. I already graduated years ago. Thank you so much.
The list of the December 6th trip.
Oh, the tour?
The tour
The tour? Wait. I'll have to ask the staff outside.